Welcome, everyone. My name's Mark Hughes, and I'm here on behalf of Royal Circuit Solutions. We're here to talk about flexible PCBs with my friends Jeffrey Lead and Teresa Restason. But before we get started, we've got a couple things to cover. First, if you have any questions as we go along, ask them down in the Q&A at the bottom of your screen. Please don't use the chat. It's just difficult for us to keep track of all of the different places you can go. So please go to Q&A. This presentation, along with the slides, will be made available at royalcircuits.com/blog within 2 business days. We're going to give it to you, so you don't have to worry about it. If you miss something, it'll be available for you. It'll also be available on our YouTube channel. If you do want a custom webinar with any of the presenters that you see today, please reach out to your sales associate, sales@royalcircuits.com or sales@aapcb.com. You do not need to be an active customer to request a free custom webinar. We'll make it for your engineering team. We'll reach out to the appropriate industry experts for your question and hopefully help you guys out. So with that, let's get going. Today, we're talking about flexible printed circuit boards with Teresa Restason of Royal Circuit Solutions and Jeffrey Leeds of Inselectro. Let's get to know our panelists. Teresa, it's our first time working together. Maybe you could tell us a little bit about yourself.
Well, hi, thanks, Mark. Welcome, everyone. My name's Teresa. I am the Business Development Manager here at Royal Circuits Santa Ana location. Royal has been around for about 20 plus years. We have 2 fab houses, one in Hollister, one in Santa Ana. We also have an assembly shop in Aurora, Colorado. Our specialty here at the Santa Ana facility is the ability to do 1 to 3 day quick turns along with full turnkey and flex, rigid flex, ATE, and rigid boards. We do it all. We also have a lot of new and exciting things happening around here. We've installed new drilling and routing equipment. We'll be adding lamination, assembly capacity with our move next door. We're also adding equipment to our wet processing area to increase capacity. Q2 is going to be huge here at Santa Ana location. Stay tuned, lots more to come.
Cool. Well, Teresa, I mean, you said it's new and exciting, and I'm newly excited. I can't wait to see it. In fact, I might just have to cruise down there to do a factory tour here in a day or two. Well, Jeff, how about you, sir? It's also our first time presenting together. Tell me a little bit about yourself.
Hey, Mark. Thank you so much for the opportunity to be on your guys' call here today. Hello, everyone. My name is Jeffrey Leeds. I am the Flex Product Manager at Inselectro. Inselectro is a stocking distributor here in North America. We have over 11 warehouses in the U.S., as well as one that has opened up in Toronto and in Canada. Inselectro supports all kinds of different substrates for printed circuit boards, everything from rigid to flexible materials, such as my product line, the Pyrolux flexible product line. I've been in the industry for a number of years, came out of college and somehow wound up working in a circuit board factory in San Jose, California, and I've stuck around ever since. My passion is always learning and trying to understand what are the new developing technologies that are out there and what materials specifically for circuit boards can help these new design requirements succeed. So for today, I'm excited to dive into just some of the basics behind flexible circuit boards and really get into some of the nuance when it comes to selecting the right materials for some of your designs.
Very cool. Well, I look forward to exploiting your knowledge, just sucking it right out of your brain like one of those little aliens from one of the Alien movies. I don't really have one on hand. All right, so as we go through, I kind of was hoping you guys would tell me the difference between flex, and rigid. Maybe we can talk a little bit about cap versus foil, how flexible PCBs are put together, where I might see a flex PCB and might start using it, how I can ensure design success, and anything else I might need to know. As a printed circuit board designer myself, I've done plenty of rigid boards, but I've not yet done one flexible. And I'd like that to change. There's some applications I've had that I just can't make a rigid make sense with. So maybe you guys can help me out.
Be more than happy to. And with that, I think, Teresa, do you want to ground us with some of the differences from a macro level between a rigid and a flexible PCB?
Of course. Yeah. So flex versus the rigid, flex versus rigid. On the top right, you can see a rigid PCB. These are the boards everyone thinks of when they hear printed circuit board. They're made of alternating layers of copper and a fiberglass epoxy mixture. On the bottom left is a flexible PCB. These are made to bend. They do away with the fiberglass layers and replace it with a high-performance plastic called polyimide. On the top left is a rigid flex PCB. This uses a combination of fiberglass and polyimide to make the boards that are stiff in some parts but bend in others, making it a rigid flex.
And with that, that's a really good macro level idea of what is the difference between a rigid and a flexible substrate. But to really get into how do we want to design, how do we want to think of a flexible board when I'm in the process of laying out and understanding my design environment, we're going to start with the rigid world and do a quick recap, no pun intended, about how we build rigid PCBs. So on the left-hand side, you can see what we normally would do, where we will take cores and then we will drill and laminate them together with different pieces of prepreg. That's what that yellow weave is in between those two copper layers. We also have another way of building a rigid PCB, and that's by doing something called cap construction or foil sequential lamination. And that's where we laminate individual pieces of copper directly onto the prepreg and we build up the core as we go. This is important because we have the ability to use something called microvias to help us break out our solvability issues we might have if we have like a high pin count BGA and we need to have multiple layers that we need to get to quickly, and traditional PCB rigid fabrication with cores on the left just don't work. When we move into the flexible world, we're going to be using a mixture of both of these manufacturing technologies to build rigid flex. And rigid flex seems to be the number one thing that most designers are being tasked with these days in terms of never designing a flexible circuit and now somehow having to figure out how to do the most complicated flexible board, which is combining the two together in a rigid flex design.
So could we go back one slide real quick, Jeff? I
Sure.
would say most of my designs these last, I don't know, however many years have been foil, on the right side, the sequential stack up. Is that going to serve me better for flex, or do I need to pay attention to how cap construction works too?
You're going to be using a mixture of both, actually, and this photo is really emblematic of that. So here we have a rigid flex PCB that's been rendered three-dimensionally so we can see the different layers. Our flexible cores are those amber or yellow lines going in between the two rigid sections. When we make those cores, we're going to be using them, we're going to be manufacturing them similar to how we do standard core construction, meaning we'll take it out of the box, we'll image it on both sides, and go through the manufacturing process. But to finish the rigid sections on either side, especially if we have BGAs, like I mentioned, that we need to break out from, we will be doing foil construction to be able to build up the number of layers and get to the density that we need. Sometimes we don't need to do that, and we might finish it with a standard core, but it really depends on the design.
That's interesting. So help me understand what it is that I'm looking at with these different layers. Like the top layer is copper. I got that. Then the next one down, would that be like a prepreg?
So
A
that would
high epoxy prepreg?
That's exactly what that would be. Traditionally, we use no flow prepregs in between the different flexible cores. That's what that red and blue weave is. And sometimes if we have to go to the really high speed world, again, we're putting really high count BGAs and we're trying to push some serious signals through one side to the other, maybe some sensors going to a FPGA on the other side. We might have to use higher resin content systems or different resin contents, doing a little bit of a hybrid construction in order to get the electrical performance we need at the surface level. So that's what that yellow weave is there. So you can do a mix and match of many different resin systems in your design, but there's certain critical areas where we need to be careful about what we're doing. We'll get into that a little bit later in the presentation, but you're absolutely correct. We can use standard resins. We can use no-flow resin systems, which is traditionally used, like I mentioned, in between those flexible cores. And then we use the flex cores in areas where, well, we need to bend.
Very cool. All right, let's hit it.
Teresa, do you want to tell us about some of the applications where we're seeing flexible circuits being built today?
Yeah, so flexible circuits are used in all kinds of applications where a normal rigid PCB wouldn't work. On the top left, you have an example of when you may need to fold up a PCB like a little origami paper for a cube satellite or a camera. On the top right, it's a flexible material used to make electric heater, which you would use to heat the seat of your car on those cold early mornings. On the bottom left photo represents the automotive industry. Flex PCBs are used extensively in your infotainment system in your car. Sorry. Anyways, and then on the bottom right, you have the flexible core to replace a rigid core in a rigid PCB. This will help shrink the overall board thickness. A little advanced design tip, but very useful when the need arises.
All right. Ooh, I see robots.
So here are some more visible, highly reliable applications for flexible circuitry. On the top right, the Da Vinci robot used in a medical field. Flexible circuits are inside all of our high-tech medical operating equipment. On the bottom left, you have the Mars rover. Flexible substrates help us save significant weight when getting the next rover out to explore another planet. On the bottom right, polyimide films and their derivatives are extensively used to protect our astronauts.
Okay, before we go on, I want a robot. That is all.
We can make that happen, certainly. Design it and we'll build it.
Nice. I like that. You're going to want money too, but hey, we'll get to that later. Okay, so seriously, these things are on Mars?
They are.
Yeah.
In fact, let's just go back one slide here. The current Mars rovers extensively use Kapton and other material sets to help not only with one insulation around that radioactive emitter in the back there, but also for all the cables that go to all the different scientific instruments. We need something that can bend all the time and not break, but we also need something that can stand up to those really cold Martian nights, as well as when you're going between planets. What is radiation going to do to our materials? Kapton has been studied extensively, and we know that it will not be damaged by ionizing radiation. Pyrolix AP, the flexible clads that are on those robotic arms, carry all of those signals back to the motherboards, and it saves weight because now instead of having a really thick cable harness, we have a nice flat cable easily packaged, and it saves tons of weight, just like Teresa said. So our descent vehicle doesn't have to be any bigger, and a rocket to get off Earth doesn't have to waste all of that fuel to get out of our gravity well and really be used to get over to the red planet quicker. There's a lot of knock-on implications for using flexible circuits, especially in high reliability environments.
That is really cool. I hadn't really considered that, but yeah, I suppose, if you do have ionizing radiation pass through, epoxy and fiberglass blend, that could set up certainly that could create a carbonized channel or, yeah, that makes a lot of sense, Jeff. I hadn't really considered that. Now I have. All right. What's next? Ooh, I like it. A little flower.
So the biggest thing here is we're talking about all those knock-on implications in the different areas we're using flex cables. But the most important thing to consider is when you're starting a new design, when do you want to get us involved? And us in this case is Inselectro and your fabricator.
Royal Circuits.
We want to be in the room with you the moment you're trying to make any decisions. We all understand assumptions made at the beginning of the design cycle, when challenged or proven to be false later on, cost immense amount of money to fix and sometimes can kill projects altogether. And here, not only at Inselectro, but also at Royal Circuits, you have hordes of engineering help for free, available to you whenever you need it. So the moment you're looking at a new design, the moment you're thinking, well, will this material work? Call us. We're here to help.
That is really cool. Do you have to be an active customer? Like, do I have to have an RFQ in the system to get that help, or?
No, you can reach out to us prior to being a customer. We're here to help.
Like, Okay, what's the catch?
There's no catch. It's absolutely free.
Interesting. All right. So I guess the next question that I would have is, what do I need to know about the materials, right? Rigid PCB, or any printed circuit board, is made up of alternating layers of conductor and insulator. Really what we're doing now is we're changing the insulating material, the dielectric material. But what else do I need to know about the different materials that make up a rigid or a rigid flex or full flex printed circuit board?
Well, there's the two types of copper. One is electrodeposited, the other is rolled annealed. The copper foil used in PCBs comes in two basic types. Like I said, the rolled annealed and electrodeposited. The electrodeposited copper is plated up perpendicular to the rotating drum, which makes it look like trees standing in a forest. ED copper can be very thin, but is also very brittle. It doesn't bend well and tends to fragment and split. To make the copper more durable, manufacturers will take thick sheets of ED foil and feed it through giant hydraulic roller presses. That serves two purposes. First, it thins the copper out, makes it smooth and ductile. And now it's oriented parallel to the plane, still like the trees in the forest, but they're long and slender, but now the trees are cut down and pointing in a single direction. Unfortunately, copper has the tendency to harden during processing. So foil manufacturers anneal the copper foil by heating it up, cooling it down. The result is the copper is thin, pliable, and easy for fabricators to work with.
All right. Where would I see these two types of foil in my board applications?
So there's multiple different places you can use an ED versus an RA foil. And when we start looking in the flex world, we're really going to start using them because of that bendability that Teresa just mentioned. So if we're doing some kind of dynamic bending event, we're going to want to use an RA foil because those grains have been squished sideways. Just like here, I'll go back one slide here. You can see in the bottom left-hand side, we've squished those grains. So when a fracture does occur, because things fail over time, the crack follows the grain boundary. But instead of being able to go straight down to the substrate and then manifest as a open in your board, instead it sees the grain from the next copper beneath the top one and it stops because that grain has been squished and moved and that fracture can no longer follow the grain boundary as it could if we were doing an ED foil. Now, you can take advantage of these properties for different reasons. ED foils traditionally can be made thinner than RA foils, and if you know you have a bend to install type of flexible PCB and you're only bending this board once, you can get away with an ED foil and be just fine. Traditionally, rigid PCBs use ED foils extensively and only go to RA foils when they need the performance. But generally for flexible circuits, we want to give them the best possible chance to succeed. So the standard for flexible cores is going to be an RA foil. Those RA foils, like I mentioned, give us a lot of great benefits from a mechanical standpoint. But when we start looking at electrical performance properties of ED versus RA, the RA foils really start to stand out. And that's for a number of reasons. On the left-hand side, you can see some examples of ED foil. And then the second one down from the top, you can see is an example of an RA foil. Now, keep in mind, I don't have the ability to see the grain boundary in these pictures, but you can see the smoothness of that foil is significantly less than that of the ED foils. And when you start looking at your insertion loss and how these factors affect your electricals, you can see on the right-hand side, we've profiled a number of RA and ED foils from multiple manufacturers and multiple coatings. And that tells us what we should expect from a insertion loss standpoint, because the signal, as the signal starts to increase in speed and in frequency, the surface roughness of the conductor starts becoming the predominant loss factor in your electricals. So the RA foils, not only do they buy us better mechanical attributes, they also buy us better electrical attributes as well.
So looking at this, it looks like the I'm trying to make sense of those two colors. It looks like 18 micrometer rolled annealed and rolled annealed 3.
Mm-hmm. So in this case, we're just looking at the thickness of the copper, not so much the distance between the peaks and valleys of the copper. That's what that equation is up on the top right-hand side. I think, Mark, you added that in there. And in this case, we're just looking at different thicknesses. So 18 microns is half ounce, 12 microns is quarter ounce, and 12 microns is a third ounce, and then 9 micron is your quarter ounce copper variance. So, you gonna say something, Mark?
I was, yeah. So I just wanted to remind people. So the equation that's up in the upper right is the skin depth for a given frequency. But I wanted to remind people that when we're talking about frequency, we're not talking about clock frequency of your boards. No, 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 no. We're talking about the frequency components of your signals. And if you have a sharp clock edge, even if it's at like 1 kilohertz, if you have a sharp enough clock edge, you can have gigahertz components. What you're looking for is the rise time, fall time. That's really what matters for digital signal propagation, not how fast the clock frequency is. And as we keep shrinking packages smaller and smaller and smaller, those rise time, fall times keep getting higher and higher and higher, or shorter and shorter and shorter. So the frequencies that you have to worry about are higher and higher and higher, even if you don't want them to be. Even if you slow your clock frequency down, you can still have those high frequency components. Sorry, go ahead.
It's good nuance, Mark. It's actually really important to point that out. A lot of things that are overlooked in designs are the copper that's being used, especially on your conductor in your transmission lines. Making sure that we give our signals the best chance to succeed is how we can make sure we can hit our design tolerances and make sure we can essentially cut down on the amount of iterations we need to build before we get a product to market. So that's an important nuance. It's often overlooked, and I appreciate you pointing that out. But there's also some other things we need to consider. We all understand that the conductor is going to be your predominant loss factor when looking at your electrical signals. But things change when we put them on a flexible substrate that's using polyimide. We change the glass transition temperature of the material, which is the point in which the material changes its expansion rate when exposed to some kind of thermal event. The decomposition temperature is the point in which materials just begin to break down. Polyimides, which are used for our flexible substrates, they don't really melt. They just kind of decompose when you start getting up to around 800 Fahrenheit. And like I mentioned before, the coefficient of thermal expansion, or ppm per degree C, is significantly less when we start looking at polyimides as well. So there's some great mechanical properties that we need to consider when building a flex board because we can use them in creative ways. But from an electrical standpoint, our dielectrics and our dissipation factors change significantly when compared to standard FR4 resin systems. And that's really what I wanted to dive into on this next slide. Here, we're just looking at the bulk properties of flexible printed circuit dielectric films. Kapton HN you can consider as your run-of-the-mill polyimide film. It's available in different thicknesses, but the most important part for all of you electrical designers out there is going to be your DK and your DF. You can see that standard polyimides are good, better than potentially an FR4 that might have a DK of around 4 and a DF of 0.02. Polyimide is inherently better because we don't have a glass weave running through our film. Our films are homogeneous, so the signal sees a nice consistent material as it flies from one end to the other in your transmitter. When we look at a flexible copper-clad circuit or flexible copper-clad core, such as Pyrolix AP, we can see that we've actually improved our dielectrics, and we've improved the DF, which is important when we move into the frequency domain for some of those really high-speed designers out there. And Pyrolix AP is really just kind of a run-of-the-mill. You can use it day in, day out, and it'll work in most situations, if not all, for your flexible or rigid flex designs. It's really important to look at your coefficient of thermal expansion if you're concerned about microvia reliability, which is a huge talking point these days. We all know that epoxy systems have significantly higher CTEs and ppm, or expansion rates per degree C, somewhere in the range of 150 to 250 ppm. And polyimide materials, because they're homogeneous and because they're different in their nature, are significantly less. So as we start to heat up a board, they stop putting as much pressure on those microvias as a rigid board would. Rigid board will expand a lot. A flexible board, not so much. When we look at something like Pyrolux HT, that's our high temperature thermoplastic film. So if you need to do something that's under hood or you're down well in some kind of oil rig, we have different adhesives that'll work in different temperature environments. And Pyrolux TK is actually a Teflon clad polyimide. So we can do all kinds of things with polyimide films that we couldn't necessarily do with rigid material and make them flexible at the same time. You'll notice that our dielectrics for these Teflon clad films are, again, another step in terms from an electrical loss performance and have a little bit lower moisture uptake. On the right-hand side, you can see something called liquid crystal polyimide, or LCP. LCP was a material that hit the market and made a lot of waves a number of years ago, but it just wasn't easy to manufacture and hasn't taken off quite like we expected. We can turn to flexible substrates and really take advantage of all of the benefits that LCP would have brought to this scene and make it manufacturable in your guys' designs today. So that's just a little overview of the electricals and of the conductors. But what does that mean when I'm trying to design a board? How do I think of these different materials and these different conductors and put them together when I'm tasked to take some wiring harness, integrate it into my rigid boards, and get the performance that I see on these different TDSs? Well, it starts with framing how we think about different flexible boards. And there's really 4 types. We have a single-sided type, a double, and a three, and type 3, which are different flavors of pure flexible boards. But the most important one that most people on the call today, I think, are interested in is rigid flex, where we're actually taking those flexible cores and we're integrating them into the rigid PCB. So with that said, how do I put it together when I'm designing a board? Teresa?
Thanks, Jeffrey. Thanks for the lecture.
Oh,
Just kidding.
Very funny.
All right. So when building a flexible PCB, we can think of building blocks for flex designs similarly to the building blocks of a rigid PCB. We have flex cores just like we have rigid cores. Flex cores are processed nearly the same during manufacturing. On the top left-hand side, you can see a SIM scan of a cross-section of a flexible core. On the right, we have a highly detailed paint cross-section of a rigid laminate. You can see the flexible clad is a homogeneous film of polyimide acting as our dielectric. On the right, we have a fiberglass resin composite, which is our dielectric. So then, but how do we stitch the flex cores together? What are the other building blocks besides cores that give us the flexibility we need? So instead of a solder mask as the final layer, we use cover lay. Why? Because it's flexible. It is laminated over the exposed copper cables that need to bend. Rather than pre-preg being used to bond the copper cores together, we use bond plies. Cover lays and bond plies are polyimide films that are traditionally coated with an acrylic-based adhesive. The polyimide film gives us a true barrier to prevent shorting, and the adhesive allows us to glue it all together. So on the left-hand side, you can see the construction buildup of those flex materials and how they would compare to rigid building blocks when designing your rigid PCB. Jeff, maybe you can explain a little bit more?
So that's a really great overview. And just like you said, well, let's get a little bit more nuanced here. How do we really put these things together? So we have the cover lay, like Teresa mentioned, and that'll be used in between our different rigid zones that you can see here. So where we have copper cables that are exposed and not encapsulated in our rigid sections, we'll laminate cover lay over those open areas to prevent the circuits from getting shorted by water or any kind of outside material. When we go inside the rigid section, we don't have the cover lay there because it's difficult to, one, bond to polyimide materials, but also second, we don't want that acrylic adhesive in the rigid zone. So we'll selectively cut that material out of the rigid area. If we have a loose leaf construction, which is what you see here, we wouldn't traditionally use a bond ply, but if we needed to glue 2 of these layers together to make some kind of microstrip transition vehicle, we would use a bond ply that'll glue the flexible cores together in the middle to make sure that our distances to ground from our signal are maintained throughout the bend and ensure we have consistent performance across our transmitter. We can use sheet adhesive, like Teresa mentioned, to build up the amount of resin we would need. So instead of buying a high resin count or a high resin pre-preg, we just put another piece of sheet adhesive into our bond plies and coverlays. And that gives us the ability to dynamically add or subtract adhesive during the manufacturing process without having to custom order really intricate or really one-off designs. We have the ability to stack everything together in our flexible areas to get to the thicknesses we need. When it comes to the rigid sections, like I mentioned before, that blue and red weave you see, that's traditionally a no-flow pre-preg. And we use the no-flow because, one, it doesn't flow very much. And during the lamination process, we want to make sure we maintain our thicknesses and that the resin doesn't squeeze out into that cover lay that we just laminated. So when you're thinking of a cross-section or you're thinking of what is my stack up going to look like, you're going to need to separate out the differences of your flex areas and your rigid areas. With that said, Teresa, do you want to show us an example of what that might look like?
Of course. So here's our stack up. And here, now that you know what all the various parts of the flexible PCB are, it's time to put it all together. That's where our stack up engineers will come into play. So as you see in the picture up here, this is one of the stack ups that our engineers have put together. So we have several stack up engineers whose whole job is to refine stack ups for your designs. They do this all day, every day. Several of our stack up engineers have been doing this since the 80s. Most of them have worked right here on the manufacturing floor. They understand the process of how our stack ups can be engineered with as few steps as possible. That is important because the fewer steps means fewer costs to you. We do all this over the phone with you for free. It helps reduce the design time and cycle time between your revisions. If you ever can or want to, please visit your fabs. Royal is more than happy to open our doors so you can come see how we build PCBs. We look forward to working with you on your next project.
It's a great overview and a great presentation. Mark, did you have something to say?
Yeah, I was going to say, if anybody has any questions, please feel free to ask them down in the Q&A and we'll ask our presenters. But I wanted to ask something specifically about this slide and stack ups. One of your friends, Chris Hunrath, told me that I should never create my own layer stacks. I should always work with the manufacturer because I don't know what materials they may or may not have on hand. And I don't want to get hit with some huge MOQ. Do you have that same opinion?
I absolutely do. The number one thing that'll hold back your prototypes or your ability to get a new design to market is whether or not those products are readily available. Your manufacturer, and in this case, Royal Flex, has a direct line of communication to a distributor like Inselectro to make sure that the design you're looking at and the thicknesses and the constructions you're interested in are quickly and readily available on the shelf so that when you place the PO and you need these boards in 3 days, we can make that happen. When we start looking at really nuanced designs, where we're using really asymmetrical copper types, we're mixing all kinds of different constructions and laminates together, we just want to double check and make sure that we can get to the closest available constructions. And we're more than happy to work with you if we need to start looking at the design and understand what kinds of trade-offs do we need to make to hit our targets. So I absolutely agree with that statement that the first thing you should do is call your fabricator and just get an understanding about what's available for your designs.
You know, is there any way I could come and watch a rigid flex board being assembled, being put together?
Yeah, absolutely. We can set up time to do a tour and show you how things are being assembled.
I really do think that would help with my understanding of how all this stuff goes together. I think I have a pretty good idea following this, but I did have a couple questions. One was that loose leaf 3D construction that we had a minute ago. Why would you do that instead of bonding everything together and making it stronger?
It really comes down to what your bend radius is. When you start bonding different things together, that changes how flexible something is. Imagine trying to bend a phone book. right? A couple thousand pages in there, really difficult to bend. You can see the different layers shifting, so you get more of a trapezoidal shape when you've bent that book. And that means in a flexible board, we don't have the ability to really expand like that. Those layers are bonded together, so they can't shift between one another. So if you're trying to bend something and you have to have multiple transition lines going back and forth between different rigid sections, we want to do what's called a loose leaf construction, which is what you see here on the slide. When we want to, let's just say, only send one transmission line from one to the next, and we do need to bond together 3 different layers, right? Microstrip construction, where we have ground, signal, ground, we can do something like this in the stack up, where you can see we'll etch off one side of the AP core, and then we'll glue it together with another AP core using a bond ply instead of a prepreg, right? And that gives us the ability to, one, maintain constant distance between our ground layers and our signals, but also, 2, we don't need to bend multiple layers at once. When you have to bond different flexible cores together in the flex zone, it's called a instead of loose leaf, we call that a bonded cable. And those bonded cables, like I mentioned, they're difficult to do. They're not impossible, but it also limits our ability to bend. And that's truly the biggest difference between a loose leaf here and then the stack up design on the right between a bonded flex cable.
Interesting. Okay. Oh, we do have a question coming in from Seth Giles. When speaking, I'm sorry, are we ready for other questions? Did you guys have more slides?
That was the end of the presentation.
So let's do some questions. Okay. And please ask these in the Q&A, because once the Q&A is empty, we will move on with life and let these fine people get back to work. From Seth Giles, when speaking of the resting position of a rigid flex PCB, is it possible to design the flexible position so that it is pre-tensioned to rest at, say, a 90-degree angle?
So we're more than happy to, I'll grab this question here. So you can actually build in and form the flexible cable to a 90-degree bend. It's done post-processing. So once you've built your flexible board, we'll actually make a fixture, and then that fixture will be laminated at not as high as a lamination temperature that we would use to co-cure the, or to cure the B-stage acrylics. But what it'll do is it'll soften up the material during that modified lamination cycle, and then as we cool it, it'll set that position into the flexible cable. So when you remove it from the jig, you'll have a nice 90-degree bend, and then you don't have to do the bend to install. You can just drop it in to your design. Or if you're trying to send a flexible cable underneath some kind of gasket or tight fixture, bending the pre-tensioning, or in this case, forming it, will help you achieve those goals.
All right. So to answer your question then, Seth, there's a way to do it, but probably not in the hot oil presses we use when we assemble these things. Andrew says, do you have basic examples of different stack ups on your website? Teresa, would you like this, or would you like me to take it?
Well, I know we don't have it on the website, but I would be happy to reach out and send him some samples.
Yeah, we're going through a website revision at the moment. So things are going up and coming down with some irregularity, I suppose. I actually have stack up samples available that I can provide to Teresa. Just basic stuff, 2 to 8 layer rigid, 2 to 8 layer flex, different types. So if you guys need some, I'd be happy to provide them to you, or we can reach out to our stack up engineers and get them from there as well. All right. Thank you, Teresa. And George asks, comment on flexible solder mask versus cover lay. Don't know if that's a question, George, but we're going to take it anyway. Jeff?
So this is something that I have seen come to the market recently, is flexible solder mask. So like we mentioned on a previous slide, instead of using solder mask like we would for a rigid board, we actually utilize, I zipped past it here. We actually utilize cover lay. And the flexible solder masks that are seen on the market today, they're not they're not at the same level that a flexible cover lay is. And there's differences to both. There's pros and cons to each of them. And at the end of the day, it really depends, which I know might sound like a cop-out answer, but it is important because looking at your design will let us know whether or not we should use one or over the other. Coverlay, like I mentioned, and like Teresa mentioned before, it's been around the block since the 1970s. And ever since then, it's been the workhorse for flexible circuits for the last 50 years because it works. Flexible solder mask is very new, and it's not something that's widely adopted yet. And there's a couple of reasons for it. But if you have any questions about it, please reach out to either myself or to South Coast Circuit or to Royal Circuits to understand how one might be better for your design versus the other. My personal opinion, I'm biased here. I think coverlay is the way to go. Like I said, it's tried and proven, but there's always other options out there. And I'm a big proponent of trust but verify. So if you have something you want to check out or see how it functions, get it something built, see the results for yourself.
All right. And I also have a quick update on our previous answer. It appears that we do have 2, 4, and 6 layer sample stackups on the website right now. So thank you for whoever sent that in. I got that anonymously, but apparently they're there right now. So download them while they're hot, folks. All right. And again, if you do have any other questions, please ask them now. We do have an anonymous question. Are there any special considerations for panelization with rigid flex designs? Jeff, would you like that or would you like me to?
So I can get in and give some guidance on it. And I think going back to this page is going to be important. When you're panelizing any flexible circuit, it's important to note the direction in which your bends will occur. So traditionally, we want to make sure that our bend is transverse to the grain direction of the copper, or to the bend direction or the bend radius, meaning when we bend, we're bending in the direction that we've squished those grains towards. So when you start looking at panelization and optimizing the amount of panels or optimizing the amount of PWBs you can put on your panel, it's important to note the grain direction and the foil direction of the copper clad. Mark, did you have anything else you wanted to expand on?
Yeah, would you bring up the stack up down at the last slide? So I just wanted to point out that oftentimes we've got to specially jig these boards. It depends on the complexity of your design. If you look at those blocks called right in the middle, LF0111, between those 2 layers, you can imagine that in a jig, that little block right there might have a piece of Teflon or other spacer material in it, so that we don't push these 2 layers all the way together, or that the 106 and 108 don't squeeze out in that direction. So there's other considerations too, predominantly the jigging. I don't know if that was the best. I thought that slide showed something else. Let's just go back one. There we go. That's better. Sorry, I remembered something else on that slide. Anyways, those spaces in between, we've got to put sheets of material in to keep everything aligned and together. We can make small panels for you. I think the smallest we can make is about 6 by 6. We're a rigid board, pretty much all of our panels are 18 by 24. We can go down, we can make a 9 by, no, that wouldn't be 9 by 11. We can go down from that too, if you need to. So we can start making these things in smaller batches for you. But really what you need to do at that point is talk to one of our process engineers who's going to have to build this thing. And he can tell you how many of them we can realistically put on a panel without really increasing the costs to manufacture this with NREs. Jeff, anything else on that?
I think that was really well put. From a manufacturing consideration standpoint, you hit the nail perfectly on the head there. We do have Teflon slugs we like to put in between those flexible cores during the last lamination process. And depending on the size of the panel, like you mentioned, it could change the way we want to design the board, or it could inflate the cost of the panel. And that's why it's really important to reach out to your fabricators to understand what those trade-offs and nuances are. So I think that was perfect.
Yeah. DFM is designed for manufacturability. It isn't just, can your board be built? It's, can your board be built quickly, easily by the least educated line workers we have on staff, right? If you need one of our expert operators that's been in the field 40 years to make your board, we've got those guys, but we got to pay them to do it. So we want to make your boards as easy to make as possible. And when I say least educated, I'm sorry, I meant least experienced. That was poor word choice on my half. All right, we've got another question, and last call for questions. From Seth Giles, can you speak to engineering considerations one might take when deciding between a flexible interconnect and ZIF connection versus rigid flex construction, price considerations, reliability, etc.? And that is not a generic question at all. It's, at what point would I use a rigid flex board versus just, doing connections board to board?
All right. Well, do you want to take this one, Mark? Do you want me to comment first? I have some thoughts on the matter, and I can speak to the reliability side.
No, go for it first, buddy.
All right. So let's just take a look from a very top line view here. So you've got some kind of ZIF connector. You're plugging it into, you're pulled apart your phone, and you can see the, those little connectors that you have a single-sided flex cable going into, which is up here what we would call a type 1. And it's important because the type 1 connector, right, you only need one side of that flexible circuit to really carry any kind of transmission or signals. Doesn't matter if it's super lossy, right? You're tapping a button on a home screen, you're turning the button that controls volume up and down. I just need to see voltage and see when something is triggered. But that's a great use case for something that might be, let's consider, high touch and might break down all the time. We wouldn't want to necessarily build a rigid flex board that has a rigid portion that's taking the sensory input in from the buttons, right? We want to put a connector there because that high touch point might break. And by utilizing a single-sided connector that we can remove and replace with, we're okay. Now, if we want to look at something a little bit different, like I mentioned before, maybe we're working inside of a telephone tower and I've got the radar dish and I've got the antenna built on a rigid section, but now I need to have a cable that goes to the FPGA that might be mounted a little bit differently and not necessarily on the back side of that antenna. In that circumstance, we really do want to go with a rigid flex design. It's not high touch. I need to make sure that my signals and all of the distances between my ground planes and signals are all kept and everything's appropriate. I don't want to rely on the fact that someone might not have tightened that connector down. We're going to build a rigid flex board. It'll be higher in terms of reliability, like I mentioned, because we don't have to worry about those connectors becoming loose, but also because it ensures some of our electricals are going to be held constant. Mark, is there anything else you would like to comment on?
I think we've got somebody's phone buzzing there in the background. Yeah, I would. Just to reiterate in slightly different verbiage from what Jeff said, if you're designing for connectivity, ZIF connect, zero insertion force connectors, and these little flex with stiffener cables are fine. But if you're designing for signal integrity, where you do have high-speed signals, going from board to board, you're kind of pushed into the direction of rigid flex, or the cheaper option, which is flex with stiffeners, right? We didn't really talk about that today, but that's the cheaper way to go. The nice thing about the polyimides is, when we say, it's 2 mils thick or 2.0 mils thick, it is 2.00 mils thick. It is exact. So when you start running your high-speed traces on one layer and your return path on the other, the TDR, if you do the impedance measurements of this, the time domain reflectometry, man, that thing looks flat. Versus if you're doing something with a rigid board, and you've got the warp and weave fabrics going back and forth, you can actually disrupt your signal integrity as the signal traverses over, high epoxy to glass, to epoxy to glass, to epoxy to glass. It just makes a mess of your signal. You can start getting eye diagrams closing. I could do a whole presentation on it. It goes nuts. But to shorten it down, just to recap, are you designing for connectivity or are you designing for signal integrity? I think that would be my my spiel. End of spiel.
That was very well put. Any other questions?
We've got some thank yous in the comments, and you know something? We would like to thank you too. This has been an absolute blast talking to Teresa and Jeff. And I believe Jeff and I are going to get into the weeds in some future webinars. You up for that, buddy?
I'm more than happy to.
Sweet. So this is kind of a high level overview, but we're gonna start talking geek stuff that really nobody in their right mind would want to know, because that's what interests us. And maybe we can even get our buddy Chris on. You both seem to have encyclopedic knowledges of material science, and it's wonderful to see. I'd love to have you around. So before we do the final goodbyes, I would like to let everybody know that next week at this time, we're going to have Mike Jupy back, and we're going to talk about thermal vias. So vias that you might put on a thermal pad of an IC, and we're going to talk about the effects, how to best design them. We might talk about IPC 7093 a little bit. It should be interesting for those of you who do work with ICs that can create a lot of temperature variation. Also, we just released a video on our YouTube with Duncan Lauder and Joe Selvik of Fixture Fab, where we talk about how to design text fixtures for your board. So after you get your board, you're going to want to test it. You're going to want to program it. They give us a rundown of how you can do that relatively inexpensively. So if you have over 20 boards, you don't want to touch those. You don't want to do all the stuff. You want to get those things tested professionally, programmed professionally, but that can be expensive. Well, they figured out kind of I don't want to call it a DIY, but it is certainly a do it with a minor assistance, so you can get started into test fixture programming creation. We're talking a couple $1,000 instead of $10,000. So it might be worth checking out. All right. Well, thank you, Teresa. Thank you, Jeff. Do you have any final thoughts?
I appreciate you guys putting this on and inviting me to your webinar here. I'm more than happy to get into the weeds the next time we want to talk, and I'm looking forward to it. Teresa?
Yeah, thanks, Mark, for putting this together, and I look forward to the next time.
All right, guys. Well, thank you so much for your time. We'll let you get back to work, and we'll see you all next time. By the way, one last thing. If you're on YouTube right now, don't forget to subscribe and like so you get notified of all of our amazing content. With that, thank you.